Hi students. In this lecture, I am going to discuss problems based on time varying magnetic field. Let us see first one. Let's see the question given. A uniform magnetic field exists in a cylindrical region of radius r. A rod of length 2L is placed as shown. The strength of the magnetic field is changing at a constant rate beta. The EMF induced across the ends of the rod is, we can see diagram here. Given field is into the board. And this is now that conducting rod. So we have to find EMF across this rod. Okay. Let us see how to start. Right. First of all, make the given diagram. Given that field is confined to one cylindrical region, and given field is now into the book, and given that rate of change of magnetic field as beta, and coming to here, it is not mentioned whether it is increasing or decreasing. Okay, assume that it is now increasing. Assume that strength of the field is increasing. Then see what we can say here. If a field strength increasing, so field is now into the board. If a field strength increasing, so EMF will be induced due to increase in flux. Okay. Then direction of current must be. That means if you imagine there is a current, that must be anti-clockwise, right? Because keeping the thumb of right hand towards us, curved fingers, it will be anti-clockwise. But anyhow, here there is no loop. This is only field is now present in a cylindrical region, and we have placed a conducting rod. It is now given like this conducting rod. It is AB, and this length is given as 2L, and radius is R. So we have to find EMF induced across AB, right? See now what we are doing. If you want to use Faraday's law, there must be a loop, right? Because if there is a loop, we can focus through that loop. Is the flux increasing or decreasing, right? So here what I am doing is, let us now join the ends of the rod with the center. Now center, take it as, it is going as point O. Join center and ends of the rod. Now if you take this AO is just like one more conducting rod, and OB also one more rod. Okay. Now see, through this triangle OAB, in this loop, the rate of change of flux. See how to calculate that. First of all, I'm focusing flux. Flux equal to, through that loop OAB. So first of all, area of base height, right? And see, coming to height, what is height? OB value, it is R. Suppose this is D, and OD value, square root of R square minus L square, right? Check it once. This is a hypotenuse in this triangle. R square minus L square under root gives OD. This is now area into field. This is now flux through that loop, right? Now rate of change of flux d phi by dt. This is magnetic flux, okay? Suffix p. 1 2 gets cancelled. This is L root of r square minus L square. This is a constant into dB by dt, and that is given as beta. This is now rate of change of magnetic flux through that loop, which is equal to EMF, right? So we are just focusing here modulus value, derivative of this one. It is now EMF. But we have to calculate across AB. Okay. Now see carefully. First of all, focus what is the EMF induced across OA. So I'm writing here EMF across OA plus EMF across AB plus EMF across OB. This total value is equal to, that is equal to E. Okay. That value we got here. So now we have to focus each value. What is EMF across OA? Across OB. If you know this two, we can get now this value. Right. Now coming to here, the electric field lines, they are closed. In fact, they are now concentric circles. That means I'm making diagram here. They are now concentric circles. And you see, while making these circles, just I'm writing here the expression for strength of the field E equal to R by 2 into dB by dt. It is inside the cylindrical region, right? If you observe carefully, up to this surface, E value is increasing linearly, right? So E value increasing means more strength means more number of field lines, right? Or you can say it is not more number of field lines. It is field lines are crowded. Strength is more. Its meaning is in that region, field lines are crowded. So here, while we are making these circles, electric field lines, first one, second field line. See, between first and second, next, second and third, gap should be less because as R value increasing, field strength increases. So we have to make separation now less. So you have to focus this very carefully. Means if you want to draw field lines, first to second separation more, second to third that we have to reduce, third to fourth we have to reduce. Relation is as we are moving away from axis, strength of the electric field is increasing. So field lines must be crowded. Okay, right. And second thing, focus on direction part. Here we have assumed that strength of the field is increasing, right? That means electric field lines they must be like this. The relation is that if I am assuming a loop like this, a loop, current must be anti-clockwise. Current must be anti-clockwise means the field lines must be like this. And direction must be in this way. Okay. Right. Now from this what I can say. Since field lines are now concentric circles, if I am taking at any point on this rod OA, direction of field will be normal to OA. I am repeating, at any point on this rod OA, direction of the field is normal to that rod length OA, normal, right? That means along the rod length, there is no EMF is induced. Okay, along the rod length OA, no EMF is induced because electric field has no component along OA. They are concentric circles. At each and every point, direction of field is normal to OA. Now, same logic for OB also. They are normal to OB. Therefore, across OA, across OB, no EMF is induced. So here what you can keep in mind is, if you are keeping a rod along the radial direction, then across that rod no EMF is induced. So this point you can keep in mind. Okay. That means this value 0, this value 0. Remaining is now across AB, and that is nothing but E, right? So L into square root of R square minus L square into beta, right? That means even though it is not a closed one, we can assume like that, a closed one. Then what happens, right? So I hope you got a clarity. Let us move for the next one. Let's see the question. A uniform magnetic field exists in a cylindrical region of radius r. The strength of the magnetic field is changing at a constant rate beta. A particle having charge q and mass m is at rest at the top of a spring constant k as shown. The compression in the spring will be, you can see diagram here, and in this you can see charge is now at the level of the center. Okay, and see why it is like that. Right. First of all, make the given diagram. Field is now confined to one cylindrical region. Cylindrical region, and field is now outwards, means towards us, and given again dB by dt, rate of change of magnetic field, that as beta. And see what is given, is it increasing or decreasing? Strength of the magnetic field is changing at a constant rate beta, right? Next, I think here nothing is mentioned, right? Okay, now see what we can do here. We are keeping at a distance L. There is a point charge. There is a point charge. It's a mass M, charge Q, spring constant Q. Assume that strength of the field is now increasing. Okay. If that is the case, how field lines are, right? Cross check once. If you imagine, if you imagine there is a conducting wire, a circular wire like this, whose center is now on the axis. Okay. If you assume a conducting loop, if field strength is increasing because of the induced current, field direction must be, it is into the board, right? I am repeating. If we assume that this field strength is increasing, then because of the induced current, direction of the magnetic field must be, it must be inwards. That means keep the thumb of right hand inwards, curl fingers. Current is clockwise. Okay. That means electric field lines also, they are clockwise and concentric, right? Then see what we can do. If you draw one concentric circle, okay, whose radius is equal to L. If I take now this as a concentric circle now, that electric field line, and this length equal to L. Then see carefully at the location of the charge, direction of the field. At the location of the charge, direction of the field, it is now downwards. Okay, I have taken this as L. That means this is L. I have taken off one field line like this, okay, concentric circle like this. That is now here. That means here force acting on the charge, it is downwards, Q into E, mg acting downwards. This is now total force acting downwards. And since it is now in equilibrium, right? See condition given, a particle having charge Q and a mass M is at rest. At rest means it is in equilibrium. So sum of these two forces must be balanced by spring force. So K into, if X is now compression, right? And X equal to 1 upon K QE, Q into E value. E value, see what we have learned, E equal to R square by 2R into dB by dt, right? This is what we got, this result, right? When you are taking outside a cylindrical region. So using that in the place of a small r, it is now L. Therefore, it is now R square by 2L. In the place of dB by dt, it is B, right? Plus mg. Okay. Suppose if you assume strength of the field is decreasing, then field and direction will be opposite. Then electric force will be upwards, right? Then we have to take mg minus cq is a pointer. If you are taking strength of the magnetic field is decreasing, then electric force will be upwards. If mg dominating, the net value mg minus qa, and that should be balanced by kx. So it depends on, is the field strength increasing or field strength decrease, right? Then see options. 1 upon k mg plus q r square by 2l into beta, right? This is option A. Okay. Let us see the next problem. A uniform magnetic field exists in a cylindrical region of radius r. The strength of the magnetic field is changing at a constant rate beta. See the first question in that. The induced EMF for the triangular circuit ABC shown in the figure. Right, first one, and condition given AB equal to BC. Right, let us see how to start. So first of all, make the given diagram. Given that exists in a cylindrical region, right? Cylindrical region. Now in that, so we are given one triangle, and it must be conducting wires. So taking one side along the diameter of that cylinder and join these ends. Right, now focus carefully. It is A, B, and C, and the condition is given at AB equal to BC. AB equal to BC condition, and rate of change of magnetic field, that is given as beta. So dB upon dt, that is given as beta. Right, first condition AB equal to BC we have taken. Find EMF induced in that triangular circuit ABC, right? In this EMF we have to calculate. So directly we can use now Faraday's law, that is E equal to minus d phi by dt, rate of change of magnetic flux. Here focus only modulus value. See what we get. No change in area, only field is changing. So coming to area, half base. See base how much? R and R, 2R. Half base height. And see what about height? This is a height, right? Let me take it as O. So OB gives us a height, which is equal to radius into dB by dt. That is now beta. So let's cancel. It is now R square beta. So it is very simple and direct, right? Okay. Now focus on next question. So that next question is the induced EMF between the ends of the length AB if AC and BC were removed. Okay, removed. Which are removed here? AC removed and BC, right? These two are now removed. Then across AB, what is the EMF induced? Then see what we can do now across AB. Let us make a diagram once again. So now having only AB, I think this kind of question we have discussed, right? See once. So now taking only AB, it is AB. So if you remember in the earlier, I have solved one question like if you connect from center to those ends A and B. So what I am doing here, just join AO and OB. It is just like earlier I have taken like question length 2L given, right? Find across AB what is EMF. Okay, almost the same question, no difference in that. So first focus what is the length of AB, right? Then see what we can say. So here condition given, see what we can say here to find O, sorry, to find length AB, right? We have to find the length AB. Let us see, can we use any result from here? Okay, I am drawing one line from O to AB, one normal. So in this OA and OB both are same equal to R. That means this angle 45. This angle 45 means let me take this as a D. Then what I can say is OD value that is equal to this is a 45, this also 45. So OD value R cos 45. Next DB or you can say AD, both are same. It is R cos 45 or you can say R sin 45, both are same, right? That means now we got length of AB, right? And I can find this triangle area AOB. So EMF equal to it is a d5 by dt. d5 by dt. I'm just focusing modulus value. It is not about sign. Area half. Base is now R sin 45, R sin 45. 2R sin 45. That is a base. Half base height. Height is now R cos 45. Okay. It is R cos 45. This is area half into base into height into dB by dt. That is beta. Right. So this can be written as you have two figures cancel. R and R square. Sin 45 cos 45 1 by 2 into beta. This is EMF induced in the triangle OAB, right? And in the earlier question, I have discussed that if you're having any rod along the radial direction, along the radius, no EMF is induced because electric field lines are concentric circuits. So direction of electric field at any point on OA, it will be normal to OA. Same thing for OB also. That's why EMF induced across AO, across OB, both are zero. Therefore, this EMF is nothing but across AB. So same kind of question already we have solved earlier, right? Let us see next problem. Right. A uniform magnetic field B exists in a cylindrical region shown dotted in figure. This is now cylinder. The magnetic field increases at a constant rate dB by dt. Consider a circle of radius r coaxial with the cylindrical region. Find the magnitude of the electric field E at a point on the circumference of the circle. Right, at a point on the circumference of the circle. Consider a point P on the side of the square circumscribing the circle. Show that the component of the induced electric field at P along BA is the same as the magnitude found in part A. So this question is taken from Hetsi Verma. Let us see how to start. So first of all, make the given diagram. So field is confined to one cylindrical region. Confined to one cylindrical region. Now inside we are taking one more circle. Just imagine one circle. Imagine one circle. Now consider one square which circumscribes this one. One square. Circle is just fitting into that square. Right. Now see what is given here. A, B, C, D. And there's a point P. So taking a point P here. Right. See the first question. Find the magnitude of the electric field E at a point on the circumference of the circle. At a point, okay. See here anything given regarding radius. Right. It is given radius is smaller. This is given as smaller. And this point, this is now inside the cylindrical region. So what we can say is now we got result that E equal to R by 2 into dV by dt. This calculation already we have done, right? Direct one. So first one is over. Now coming to second one, consider a point P on the side of the square circumscribing the circle. Show that the component of the induced electric field at P along BA is the same as the magnitude found in part A. Right, now see what we can do. So here we can join the center of the circle to this point. Okay. See here what I'm doing. I'm drawing once again that. Or take that square here separately. Take that square A, B, C, D. Now we are taking a point on this square. So take a point P on the square. Let us join this center to P. Let us consider now this distance as R dash. Okay. And if you observe carefully, direction of field line, for example, in this what is given, magnetic field increases, right? And direction of field is into the board. So field increasing in such a case, electric field lines. See what we can say, field is now into the board. Then field lines means if you imagine there is a conducting loop. If you imagine a conducting loop here, current must be in such a way that because of that induced current, magnetic field must be outwards, right? That's why I am keeping thumb of right hand outwards, means towards us, curled fingers. Current must be anti-clockwise. That means field lines, electric field lines, if I am taking, they must be like this. Electric field lines must be like, so direction part must be like this. Concentric circles, direction must be like this. If I am taking at this point tangent, means if I imagine one circle, by taking now r dash as radius, at this point, direction of V bar will be normal to OP, right? It must be normal to OP. Let me take it as E dash. Okay. That means if I imagine a circle of radius r dash, then E dash will be r dash by 2 into dV by dt, right? Because this point is now inside the cylindrical region. Okay, right. Now he's asking, it's a component along AB. It's a component along AB. Let us join this point O2. O2B means I'm taking a normal to AB, and let us consider this angle as theta. Okay, if this is a theta, this also theta, right? Check it once. For this line, this is normal, and for this line, this is normal. So between the normal same angle, this also theta. That means we have to prove that E dash cos theta is equal to E. This is what we have to prove, right? So E dash R dash by 2 dV by dt. Okay. Next, see what else? Cos theta. Cos theta means this is now R, right? This value is R. So cos theta will be R by R dash. R by R dash, right? That means now see what happens here. We can cancel R dash and R dash, right? R dash, R dash. Remaining is R by 2 dB by dt, which is nothing but E, right? That is what we have to prove. Okay. So I hope you got the clarity.